This would be it for theory. Let's now see it in practice. The everyday use of the solutions is as follows. Symmetric ciphers have their shortcomings. The biggest limitation they have is they require managing a huge amount of keys and don't offer the option to exchange them. Non-repudiation and authenticity cannot be assured either. Asymmetric ciphers, on the other hand, are not useful for encrypting long messages. They are slow and inefficient, but solve the key exchange problem and provide for the ability to prove a sender's identity and establish the authenticity of a message. By combining the best of the two solutions, you can arrive at a hybrid cryptographic system. All systems today in fact use a hybrid scheme. SSL, EFS, and HTTPS all use hybrid cryptography. The idea behind it is that while messages are encrypted using symmetric cryptography, the keys used for encryption are encrypted using asymmetric cryptography. The keys are put in a digital envelope and sent along with the ciphertext. The word send is used in a broad sense. It doesn't require, for example, sending data over a network between users A and B. The data can also be put on a disk. The message circulates in time until someone finds it and decrypts it. So let's take a look at the encryption process in a hybrid system. You have a message that must be encrypted using symmetric cryptography. For example, using the Advanced Encryption Standard. To do this, you need a key. Let's call it a symmetric session key. It will be pseudo-random and secure. You have successfully generated it. Next, you should asymmetrically encrypt the generated symmetric key, using, for example, RSA or Algol. The output is saved with the ciphertext. This will allow you to include copies of the key that are encrypted using other system users' keys. If the ciphertext is intended for 6 recipients, you should repeat the operation 6 times. The recipient's public keys will be used for encrypting the session key. The number of session key copies matches the number of recipients. Each copy is encrypted using a different public key. How do you decrypt this message? You get a ciphertext. To start to decrypt anything, you need to have a key. An encrypted session key has to be taken from the envelope. Decrypt it using a private key. There's a private key that corresponds to the public key, which means that only an authorized user can perform this operation. The user is the intended recipient of the message. If you have a session key, the remaining process is straightforward. Decrypt the message using symmetric cryptography. The output is the original text of the message. By the way of ending this module, let me say a few concluding remarks. Remember that developing a cryptographic system is always difficult, and creating a cryptographic system that is secure and non-vulnerable is perplexing and nearly infeasible. Don't use algorithms you designed yourself in a production environment. While developing or modifying cryptographic algorithms can be a great intellectual diversion, if you're not a professional cryptographer, if your work hasn't been entered into a competition and tested by experts in the field, don't even think of using it in a computer system. The same reservations can be applied to using classified ciphers, following Kirchhoff's principle. And even if you decide to use a well-known and tested algorithm that has an appropriate strength, don't experiment with implementations of the algorithm modes of operation. Don't fall into the trap the electronic codebook fell into. The mode uses the advanced encryption standard, long plaintext inputs that you split into blocks on your own, and then apply encryption. Don't do this. Even the relatively weak algorithms like RC4 that are vulnerable to adaptive known plaintext attacks, if implemented correctly, are resistant to the threats. Even a slight modification, for example adding an additional round or an additional permutation, don't modify things on your own. Apart from this, keep in mind at all times the crucial rule. Your system is only as secure as the weakest element. System vendors often try to obscure this by claiming, for example, that their solution guarantees total security because connection to some bank service requires using a 4 kilobyte RSA key. What they hide is that a 4 kilobyte key is then used to encrypt a 56-bit DES key, and that the following transmission, which is symmetric since a hybrid scheme is used, proceeds with the weak and vulnerable DES algorithm. A potential attacker will not try to crack a 4 kilobyte RSA key. They will directly target the DES encryption. Thank you for your attention.